Thank you very much. As Alan alluded to, this is not about the delicious Caribbean beverage that some of you will be enjoying this evening, but about stories of real-world mobile performance, where RUM stands for real user measurement or real user monitoring, depending on who you talk to. So, already got a bit of an intro from Alan there, but my name is Peter. I'm the Chief Product Officer at Mobify. Mobify is a software as a service company that makes responsive websites faster or takes existing desktop sites and makes them responsive with one line of JavaScript. In the last year or so, about 2.5 billion people have visited a Mobify-powered website. So why is mobile performance even all that important? Why do we really want to talk about this to begin with? If your website got 10 or 15% of its visitors on mobile last year, you're probably looking at getting 20 to 25% plus this year, and in the next couple of years, we're probably going to see the whole pyramid go upside down, and you may be getting 50+% traffic from either tablets or smartphones pretty soon. This makes mobile performance matter quite a bit, if not perhaps even more so than your desktop performance pretty soon. There's also a lot of unique challenges that come with mobile performance, not the least of which are problems around radio links, lower bandwidth, higher latency. We'll get into a little bit more of that later on. If mobile performance doesn't inherently sound that exciting to you, think about it in terms of what the cost is to the world of having slow websites. So if you're working on a website that's moving any significant amount of traffic and it's taking a bunch of extra seconds to load, and you imagine people are visiting lots of these websites during their day, you're actually consuming an awful lot of time. Now, that time may or may not have been put to more productive use. Maybe people are not going to be doing anything productive with it at all, but at least they'd have a choice about spending their time on something else other than waiting for your website to load. I think that's a pretty good reason to make fast websites all by itself. If you want a slightly more monetary reason, there's a bunch of research. This particular little bit comes from Kissmetrics. Amazon's released some pretty similar numbers. 1 second delay in e-commerce site, 7% reduction in conversions. If you're not running an e-commerce site, this still applies to you. Any goal-oriented website, and I tend to think that the vast majority of websites are up because they had some sort of goal. You're going to see a penalty if your website is slower than it has to be. So for every extra second that your website takes to load, less people are going to complete your goal, probably in a ratio not dissimilar to the number that you're seeing in front of you right there. So what's changing about the landscape here, and what's so interesting about this particular chart? We have a bunch of wireless technologies here, starting with 3G on the left, going up to LTE on the right, a couple of different varieties of HSPA Plus in the middle. And you can see here that we have more than 10x'd the performance of 3G with LTE. Now, I know that a lot of you are going to say, well, I don't actually see 75 megabit per second on LTE. Obviously, these are theoretical speeds. But the fact, one thing's pretty undisputed, and that is LTE is a lot faster than 3G. So what is interesting about this when it comes to web performance? I'm sorry to say that not a whole lot. It's absolutely awesome that you can stream video over LTE. That's fantastic. That's exciting. You can do a lot of cool things. I'm definitely not complaining about having a lot of extra bandwidth. But, whoops, a little too far there. This is the reason why we're not seeing massive performance improvements with technologies like LTE. On the chart on the left, what you're seeing is page load time related to amount of bandwidth available. And something that you might find pretty interesting is that there's an inflection point right around 3-4 megabit per second where it starts to flatten out and the gains get really incremental with additional bandwidth over that. On the right, we have page load time again, this time mapped around decreased latency. And here we have almost a linear relationship between decreasing the latency and improving page load time. So here's the problem. We've made a 20 times gain in the amount of bandwidth available. We have not made a 20x gain in the amount of latency, in reducing the amount of latency for web requests, nor are we very likely to. There are hard limits on that, like the speed of light, that are not going anywhere anytime soon. And we're making improvements. Like, there are incremental improvements. LTE has lower latency than 3G, for example, and that's just related to the radio link technology. So this is improving, but we're not expecting to see any kind of 10x improvement in this in the foreseeable future. And if we do, you can look forward to meeting some future version of yourself who came back in time. So what are the standard things that people say that we should actually do about this? So this is just kind of a list taken from the Yahoo performance rules. combining files. Most of these things, like the top 4 things there, are all about reducing the number of HTTP requests. So it's like, okay, we accept that latency is a problem. How are we going to deal with that? Well, we're going to ask for fewer things so we don't have to pay this latency cost again and again and again. Use a CDN, all this stuff. You've probably seen lists like this before. This list comes with a bunch of usual problems. That is that websites are not the same. You could take any one of these pieces of advice and say, this is a good idea for this website and not a good idea for that website. And there are even things that seem like they should universally be a good idea, like a CDN, and I can give you an example of where a CDN is not a good idea. Let's say that I ran a website that was about places to eat in Vancouver, and I had a well-configured web server here in Vancouver. 95% of my visitors are in Vancouver. Would it really make sense for me to use a CDN whose closest edge node is in Seattle? Absolutely not. I'm just adding another piece of complexity, a lot more round trip that needs to happen potentially if I can't cache my content at the CDN layer. And generally speaking, I'm probably not going to be helping my users out by using a CDN. If I'm doing a good job with serving directly off my infrastructure here in town, there's not a good reason to use a CDN. So basically, RUM is the answer to this. What we need to do is actually look at what are the behavior and what are the performance characteristics that we're actually seeing from real users on our website. So this is a good opportunity for me to introduce a little bit more about RUM if you aren't familiar with it. One of the reasons why talking about RUM is a great fit for CascadiaJS is because RUM is usually done using client-side scripting. So it's usually in JavaScript, in the browser, measuring things. And by things, that could be literally anything that can be measured with JavaScript. It could be load timing for particular elements. It could be page events. Anything that you can think of to measure gets collected using JavaScript, gets sent back to a backend server for analysis and processing. That's RUM. The biggest advantages to doing things this way are that you get way more scale than you could possibly achieve if you were doing this in a laboratory. So let's say that you have access or have a device lab. You probably still only have 25, 50, 100 devices, and you've got a lot of spare QA time. Okay, you can do some synthetic testing. You can write tests and kind of get an idea how things are going to work. You're still never really going to get the incredible variety of devices, connectivity options that you're going to see in the real world. And when you start going out to the real world, that's when you start to see some really interesting things. So let's talk about what some of those interesting things are. I'm going to start down at the network layer. Simple test. State of the union in terms of mobile performance. Let's test how long it takes to get 0 bytes of data via an HTTP request. That means just headers, back and forth, completely empty body. I'm going to create a brand new domain for this, so there's no cookies, there's nothing else involved. This 0-byte file is going to be served from a CDN, so it should be relatively well distributed in terms of edge nodes across the country. Nobody should be too far away from one, and see how long it takes in various countries for that 0 bytes of data to arrive. Now, keeping in mind, this is what we call a cold TCP connection. So in this case, the connection has not been established. It's a brand new domain, so there's going to be a DNS lookup. So we've got DNS lookup, connection, HTTP headers back and forth. You can see here that we're coming in largely grouped just under 250 milliseconds to do this. By the way, if you're wondering about the DNS part, that's also done via a distributed Anycast network. So that should be about as fast as could be reasonably expected as well. These numbers should probably seem a little bit high to you. We'll talk a bit more about why that is in a second. I was curious, this is really just kind of a point of interest, is there any differences between browsers? It's not really about something specific to the browser with respect to this test. It's really just, do people who use these different type of browsers kind of have different connectivity? And the answer is a little bit, not a lot. It's kind of interesting to see that Firefox users seem to have slightly better connectivity than some of the other users. It's also the smallest sample size of the lot. For most of this data, I didn't put the sample size in the slides, but we're talking about having a few million data points for most of these. If you're curious, please talk to me after the talk, and I can get you a more precise number for each of these measures. But generally speaking, yeah, there's not a lot of difference between the browsers in terms of their connectivity. Pretty similar. All right, this isn't so great. I mean, 200 to 250 milliseconds to download absolutely nothing. That's not really fantastic. Google says websites have an average of 42 resources on them. So you can imagine that if we were doing things really naively and we were actually serially loading 42 things, we're talking about websites that are going to take a minimum of 10 seconds to load, and that's assuming that you're loading 42 empty things. If you actually have data, that gets even longer. A few points of optimism here. That connection is cold. Hopefully, you're not always reestablishing cold connections. It does include a DNS lookup. Usually, you should only have to do that once. So let's see what happens when we start bringing warm connection and data in here. 6.7 kilobyte image downloaded, broken down across countries, and we see both the warm and the cold connection state. Why a 6.7 kilobyte image? Google says this is the average size of an image on the internet. That's kind of surprising, but I guess it makes sense if you consider that there are lots of 1x1 pixels and other things that are quite tiny out there, probably skewing things downward. So here things are looking a little bit better. If you notice in the warm connection state, we're actually down closer to 100 milliseconds round trip for transferring this thing, 6.7 kilobytes. That's still kind of high, but it's a whole lot better than that kind of 250 milliseconds that we're talking about for the cold connection. Point of interest, how does this break out over some of the big ISPs here in North America? Interestingly enough, we are pretty fortunate here in Canada. You'll notice that Bell Canada and Rogers networks are actually right up there near the fastest. Sorry, Sprint, things aren't looking so good for you. But they're actually clustered pretty close together, especially in the warm connection state, where you're looking at roughly 150 milliseconds or so. So what other things can affect HTTP performance? Let's have a look. Cookies increase the size of the HTTP request header. I'm pretty sure that almost everyone in the room should know what a cookie is, but in case you don't, it's a tiny bit of information that's attached to the request and response header that's intended to help preserve state information. And usually, this is a very small amount of information, but it could be up to several kilobytes. Now, if you haven't really thought about it, you probably think, well, what's a few kilobytes? It doesn't really matter. Most, even smartphone websites these days are 1.5 meg, 2.5 megs big. So what does it really matter if we're passing back and forth a couple of extra kilobytes? This is why it matters. So the thing you want to look at right there is that purple box that says data. And underneath it says MSS. That's maximum segment size. This could actually vary by carrier. Could be between 576 and just under 1,500 bytes. And this is basically the payload that can go inside of an IP packet. You really want your request headers to fit entirely inside of this MSS. Why? Because if it doesn't, the web server has to wait for the next packet to arrive before it can even begin processing the response. So basically, you have a request come in, the server receives the first packet. If the request is split across multiple packets, it's going to sit there, and you've got a head of line blocking problem. Web server can't do anything. It's got to wait for the rest of the request to come through, because who knows, there might be some other piece of important state information in the rest of the request headers that's going to affect its behavior. So it doesn't have any choice. It has to wait. Your worst case scenario on a cold connection, let's say you're dividing over 2, 3 plus packets, we have another thing happening called TCP slow start. So TCP slow start, I'm absolutely not going to really get into the details of how this works in this talk, because you could give an entire talk about it and then some. You can think of it as the internet traffic cop. It's there for a reason. It's by design. It's not some sort of defect in the internet. It is there to allow routers to do their job, control congestion on the internet so that everyone gets their packets in the most expedient way possible. But it does mean that when a new connection starts, it tends to start slowly. So if you're establishing a new connection and you're overflowing and you're splitting your HTTP headers in your request over multiple packets, you're going to see a performance penalty. What kind of penalty are we actually talking about here? On the order of probably 10, 15% if you go up to a fairly hefty size of 4 kilobytes. Now you notice that I put a middle condition in there, which is green, which is 400 bytes of cookies. This actually came out of a Google page speed recommendation for the maximum number of cookies that you should have. And you could see from this graphic that their advice looks pretty solid. When you go from not having any cookies to 400 bytes of cookies, the difference in performance is almost negligible, like a couple percent maybe. When you go up to 4 kilobytes, we're starting to see some pretty significant penalties on the order of kind of 50, 60 plus milliseconds. So what about in the warm case? Now here's where things get kind of interesting. The scale has changed on this graphic, but relative to the previous one, it's about half. So in terms of absolute time, this has gone down to about 25 milliseconds in terms of what the penalty is for having 4 kilobytes of cookies. But in terms of the relationship of the performance impact, it's actually making a much bigger impact on the warm condition when you have a large set of cookies. So we're up to about a 20 to 25% performance impact here. So definitely looks like there are gains to be made here. It's not a huge performance win, but if you've exhausted other options, you know, a free 15, 20% performance gain is not a bad way to go. And the way to take advantage of this, most often recommended way of doing this, is to have what's called a cookie-free domain for static assets. So you basically just register another domain name. They're pretty inexpensive these days. It can literally be anything because it's not going to be in the URL bar of your site. And just put all your static assets there. And the back end can be the same server as your regular domain name. And that'll give you the ability to serve these resources without any cookies. You know, 99% of the time, the images and scripts on your site, etc., shouldn't actually have any, you know, context-sensitive back-end processing going on. So you should just be able to serve them cookie-free without any state information attached. So I mentioned that there were 42 resources on the average web page. You know, not to question the authority of Google, but that actually seems pretty low to me. Most of the waterfalls that I look at day to day have a lot more than 42. They're more like 80, 160. I've seen like 200, 300 plus on some sites that will remain unnamed. One of the ways that browsers try and improve the situation is by downloading more than one thing at once. Makes a lot of sense. Then we don't have to pay this cost serially. We can just download a whole bunch of things and just kind of pay that 200 millisecond penalty once, hopefully. HTTP 1.1 spec said that there should be 2 requests simultaneously per host name. Modern browsers ignore that completely, and you can see here that Safari and Chrome Mobile both use 6 simultaneous connections. The Android browser, Firefox Mobile, use 4. Actually, that number for Firefox might be out of date because I did this about 3-4 months ago, so they may be up to 6 or some other number now. The way that people have tried to work around some of this parallelism is they try to hack parallelism by upping it using something called domain sharding. And this technique basically involves dividing your static assets of your site over a bunch of different host names, and that will cause the browser, not force it, but cause the browser to connect, open its maximum number of connections with each of those host names. So let's say you had, you know, shard1, shard2, shard3.yoursite.com. The browser's going to go and open that number of connections. But this optimization was really made for when browsers did obey that maximum 2 simultaneous requests per server rule. It doesn't make a lot of sense now that they're opening 4 or 6. So if we look at what happens here, simultaneous connections, when you have 2 shards on, say, Safari or Chrome Mobile, we're now talking about the browser opening up 12 connections. Why is that probably not good? Well, you remember that chart back there about the difference between performance between a cold and a warm connection? Well, basically, you're paying that cost of a cold connection 12 times now instead of 6 times. Things get even worse if you were to go up to, say, 4 shards, where you're now paying that cost 24 times. That's essentially a fixed cost to establish the connection and then move the first few bytes of data to warm things up. So what happens when we actually test this? Let's give it a shot and see what happens when we download 14 6.7 kilobyte images. And you can see here that we are looking at a performance anti-pattern on mobile. It's not a strong anti-pattern. You notice the difference, probably the strongest difference is in iPhone Safari, where we're seeing maybe a 5–10% penalty for going between having a single host and 4 shards. But across the board, and pretty much, it's some kind of penalty. From this, I would say that sharding's probably not going to help you. It may hurt you. Just applying the KISS principle, keep it simple. You should probably avoid doing this if you aren't doing it already. And if you are doing it already, you should probably plan at some point in removing it. HTTP 2.0 is going to take this from a you probably shouldn't do this to please do not do this. HTTP 2.0 introduces connection multiplexing, which allows multiple things to be simultaneously sent, multiple resources to be simultaneously sent over a single connection. And that means that this is going to be, that opening more than one connection is going to be a major anti-pattern when HTTP 2.0 drops. So, this is early notice. Should probably be migrating away from doing domain sharding. Let's talk a little bit about images. What does it mean to actually materialize an image? This is really trying to look at different ways of bringing an image, of making an image appear in a browser. And you're probably familiar with the most common way of doing it, which is to just have an image element, set an SRC that is a URI to where that image can be loaded from. It doesn't really matter whether you're doing this in JavaScript or straight in your HTML. It's basically the same thing. Another way of doing it is using a data URI. So that would be, you've got this base64 string attached to the SRC attribute of the image. And then you can basically do exactly those two things again in CSS using some sort of block element and a background image assigned to it. Again, you have the option of either a data URI or a direct URI to some path on the internet. This is what we see when we actually test using a real set of images. So in this particular case, I decided to test with the Amazon sprite set. So if you go to Amazon.com, they have a sprite that contains 39 images. So what I did was I broke those images out, turned them into data URIs, and tested to see what the performance difference was between having 39 data URIs versus having a single sprite. In both cases, it's one external HTTP request to either download the CSS containing 39 data URIs or download the CSS sprite. I think what's most interesting here is you can really see, you can eliminate kind of all network-related stuff when you look at the cached condition. So you look down there at the cached condition, and I ran this before iOS 7 drops. So that's why you see iOS 6 down there. You'll notice that on iOS 6, it's actually about more than 2 times faster to use a sprite over a data URI. This is probably something that browser vendors are looking at. When I talk to some people from the Chromium team, they're going to have a look and see why this is the case. There's really not a fundamental reason why data URIs should be slower, but these are the results that we're seeing in the wild today. Something else that I wanted to look at was what are opportunities to improve performance around CSS. So a couple of years ago, some of you may have read this blog post from Steve Souders. He's kind of a performance guru from Google. He did a test to see whether or not there was any advantage in optimizing your CSS rules. His test was run in 2009, and it consists of just a very simple web page. It has 2,000 tags in it. More than 2,000 tags. It has 2,000 anchors that are nested in other tags, and it has 2,000 CSS rules. He created 5 conditions. The baseline condition, where actually there are 2,000 CSS rules, but none of them actually match anything in the site. Then there's one where there's a tag rule, and that will match all of the anchors there. The class rule, where there's one class that will match a single anchor. Child rule, which you can see there, where we're going through a chain of 5 child selectors, and then a descendant selector condition. And he just wanted to know, should designers have to worry about the performance of their CSS selectors? Something else that I think makes this relevant is that a lot of us these days are using Sass or other CSS generators that if you're doing a lot of nesting, can actually, if you ever looked at the output that's coming out of there, you'll notice that it's probably pretty ugly. You can get some pretty gnarly looking selectors generated out of this, and you may or may not really be aware of that when you're writing those style sheets at a high level. These were Steve's results. The specific results don't really matter nearly as much as the fact that all of these lines are pretty flat. You'll notice that things do kind of skew a little bit upwards in terms of time to complete the test towards the right, but it's a pretty marginal difference between the baseline condition and the condition where we have the descendant selector, which really should be the slowest. His conclusion was you probably shouldn't waste your time optimizing your selectors. So I thought, what about mobile? Let's just run exactly the same test again and see what things look like. Looking pretty similar. You'll notice that definitely the older Android browser is a fair bit slower overall, but that's probably less about the browser and more about the fact that newer Android smartphones are coming with Chrome pre-installed. So we're probably just looking at older phones overall, so less CPU power available to them, more than the actual performance of the browser itself. Something else you might notice, Firefox is really fast. And the only browser where we're seeing any kind of significant, and it's not even really significant, any significant difference between baseline and descendant is actually Chrome, a tiny little bit on Safari. For this particular test, I lumped Safari 6 and 7 together, so that's why you see Safari 6 Plus. But it's pretty small. Like we're talking about the difference between 500 milliseconds to render versus 550 milliseconds to render, less than a 10% performance difference overall. Do you have to worry about this? There are probably a lot of other optimizations that you should be thinking about doing before you worry about optimizing your CSS. I will say it's too early to say don't worry about CSS at all. There are things you can do in CSS that are really, really bad. For example, we discovered one website that was using the backface visibility applied to the selector star. This was basically blowing the performance of the site out of the water. In terms of frames per second of the rendering, when you scroll down the page, it was noticeably chunking along. And the reason for this is the way that this engages the GPU for each element of the page when you apply it this way. There are other things that are going to probably have an impact on your CSS performance. Things like conditionals may impact performance. There's a lot more testing that needs to be done here. So just to kind of wind things up and just put in one slide the kinds of lessons that I'd like you to take away from this talk is that latency is a big problem. It's not going anywhere. You really want just enough connections so that you're reusing warm connections as often as possible. So something you might want to talk to your server team, your DevOps team about, possibly your CDN, is what kind of timeouts are they setting, both at the kernel level and the HTTP server level, that are saying to clients how long can they hold a connection? Because the longer they can hold a connection, the better. There's a trade-off there. You don't want to make that too long, or your server's going to run out of sockets. But definitely, you want the server to be allowing connections to hang around at least for a little while. Use less than 400 bytes of cookies. In a perfectly ideal world, use a cookie-free domain for any asset that doesn't actually need to have state information attached to it. Domain sharding bad, CSS sprites good. And don't really sweat your CSS selectors too much, but do watch out for CSS that might engage GPU. Probably avoid the star element unless you really, really need it. And keep your eye out for other like conditional CSS rules. Just to conclude, there's tons more work that needs to be done. These are very early days. What I'd love to see is a lot more community effort around measuring things in the wild, aggregating that, and sharing that knowledge with developers, and also working with the browser teams to address, some things are inherently slow, other things don't have to be slow and could be improved. Thank you so much for listening. I hope to speak with you at the break.